Okay, for this video, it is module 30 still, I think video 3 now. So multiplying expressions involving complex conjugates. So they want me to multiply this out. Before I multiply it out, there's two ways you can do it. I prefer to just get rid of the double parentheses and then just FOIL it all out, okay? It's just a little bit simpler for me to do that. So if I distribute this minus, this first factor becomes x plus 1 plus I. If I distribute the minus here, I get x plus 1 minus I. And then if I just FOIL everything out, it'll play out what it's supposed to do. So that's positive 1x minus ix, positive 1x, positive 1, negative I, positive ix, positive I, negative I squared. So then I get, let's see, negative ix and positive ix will cancel. Negative I and positive I will cancel. And I end up with x squared here and here. So that's 2x plus 1. And this is really a minus negative 1. Or it's the same as saying plus 1. And so my final answer is x squared plus 2x plus 2. Okay, so the same thing here. This one doesn't have a double parentheses, so it's actually easier. So I'm just going to FOIL it out. X times x is x squared. That's negative 3ix, positive 3ix, and then negative 9i squared. The negative 3ix and the positive 3ix cancel. Here I get x squared 9 times negative 1, which is the same as x squared plus 9. And you don't have any like terms to combine, so you're done there. The next problem says find a polynomial given degree with given zeros, and you're given complex zeros. Now, the one thing that we have to figure out is that notice here when you multiplied two conjugates together, you ended up with a polynomial that only had real coefficients. Same thing here. You multiplied two conjugates together, and you ended up with a polynomial that had real coefficients. So what that tells us is about the conjugate zeros theorem. It tells us that if you have one complex zero, then you automatically have its conjugate also as a 0. Because that's the only way you'll get real number coefficients later. Otherwise, if I just have one imaginary complex 0 in there, it's going to leave a bunch of i's in my polynomial. But my polynomial is supposed to have real coefficients. Okay? So even though they only gave me 2 zeros here on paper, they actually gave me a third because according to the conjugate zeros theorem, automatically negative 2i is also a 0. So there's actually 3 zeros that they've given me. And since my function is supposed to be of degree 3, I should only have 3 zeros. So that means I have all 3 that I need to be able to write the function. So let's go ahead and write it. That means if these are zeros, then x plus 1, x minus 2i, and x plus 2i are the factors. Now I do need to multiply all of this out because they do want me to write it with real coefficients. Right now I don't have real numbers in here. Okay. The best way to do that when you're multiplying these out is to multiply the conjugate factors together first and then multiply the other factor. So I want to multiply these first, and I'll multiply the other one, x plus 1, later. for this product, we get x squared plus 2ix minus 2ix minus 4i squared. These will cancel, and this just makes that a plus, so I get x squared plus 4. That negative I squared, or I'm sorry, the I squared just ends up changing this sign, right? Because it's a -1, and a negative times a negative will give me a positive. Now I'll just FOIL this out. So I get x cubed plus 4x plus 1x squared plus 4. And if I want to write it in descending order, I would put the x squared next, then the 4x, and then the 4. And this is the answer that they're looking for. Okay, here it's the same topic, but now they gave me these zeros. And so we know automatically by the conjugate zeros theorem that the conjugate of this is also the 0, which would be the third one. 1, 2, and now we're going to write the third. The conjugate of this is the real part stays the same sign. The imaginary part is the part that changes sign. Right? You have a plus bi and a minus bi are conjugates. So notice the real number does not change signs. It's only the imaginary part that changes sign when you're writing a conjugate. So let's write out the problem in factors. So x minus a minus 4 is plus 4. And then x, and change all of these signs. So positive 3 minus I, and then positive 3 plus I. Remember, whatever the signs are in your zeros, you're going to change those signs when you write them as factors. So let's multiply the imaginary ones together. Uh-oh, I'm confused. Okay, so x, 3, ix, 3x, 9, 3i, minus ix, minus 3i. I lost myself there for a second. So then now let's see what cancels. So negative ix, positive ix, negative 3i, positive 3i. And then this is just a minus -1, so it's really a +1 here. So 3x and 3x is 6x plus 9 and positive 1 is going to give us positive 10. And then I can FOIL those out. And I get x cubed plus 10x squared plus 34x plus 40. And this is the function that they're looking for. Okay, we're on our last topic of Module 30. It says using a given polynomial or a given zero to write a polynomial as a product of linear factors. However, I will end up with complex zeros. Okay, so we do need to do just like we did before when we had real zeros. We're going to take out the -1 and see what that looks like. So cube is the highest, 1 squared, x's, and constants. Bring down the number, multiply, -6, multiply, +6, -4, no, that would be +4. Then when you multiply, you get -4 and you get 0. And then this is your A, B, and C for the quadratic formula. And since they're telling us we're going to have some complex zeros, I'm assuming they're going to come from the quadratic formula here. Now, I don't know if I wrote this problem down wrong, because it doesn't look like I'm going to get complex numbers at all. In order for me to get complex numbers, the inside of that square root would have to be negative. And I am not getting a negative. So I'm guessing that in this particular topic, you could or you could not get complex zeros. So I don't have any imaginaries here, so there's no complex zeros in this particular problem. But I do have to still finish the problem out and write it as factors. So it becomes x plus 1, x minus 3 minus square root of 5, x minus 3 plus square root of 5. Again, taking these two numbers and then changing the signs on both terms there. Okay. So that one didn't actually yield us any complex factors here. But let's go ahead and do the next example, and maybe we will discover some complex numbers here. So here we have an x to the fourth, and they give us two numbers. What that means is we'll have to do the synthetic division twice. Okay, and I'll show you how to do that. So the highest is x to the fourth, so x to the fourth, x cubed, x squared, x, and then my constant. So let's play out the synthetic division. And it does not look like I'm getting the answers that I should be getting, but let's keep going. No, I'm wondering if I wrote these problems down wrong. Give me 1 second. Okay, so I noticed that I'm not going to get 0 even though they're telling me that this is a 0. So I should be getting 0 here. So these were obviously some bad problems. So I'm going to go ahead and redo this topic on another page if I can find one. I cannot. So I'm going to pause real quick and I'm going to erase everything that I have and write down two polynomials that this should actually go with this topic. I have no idea where I came up with these. I probably wrote down a typo somewhere, but let me fix it. So I'm going to pause the video. Okay, so here are some other problems. This is the same topic, using a given 0 to write the polynomial as a product of linear factors. We've done it already before with real numbers. Now we're supposed to get complex numbers here. So the process is still the same regardless of whether you end up with reals or imaginaries. So I'm still going to put 1 on the outside. And then x cubed is my highest, then x squared, then x, and then my constant. And start the process. So I get 1, I get 2, I get 2, I get 26, I get positive 26, and so I get 0. And so then again, what I'm left here with is my A, my B, and my C. So if I do my quadratic formula, So if I want to bring that negative out, it becomes an I. And then the square root of 100 is 10. So we're supposed to write this as negative 2 over 2, and then that formally is 10I over 2. So we get negative 1 plus or minus 5I. So we have 1 is a 0 that they gave me, negative 1 plus 5I is a 0, and negative 1 minus 5I is a 0. So if I want to write this as factors, it's going to be x with a negative 1, x with a positive 1, and a negative 5I, and then x with a positive 1 and a positive 5I. And that's the factored form. So finally we did up with our complex numbers here. Now, in the other example that I had previously before I changed it, it had two zeros here. It had negative 3 and negative 2 or something like that, but they were explicitly given, okay? Here, I'm not explicitly given two numbers, like 1 and 2, right? I'm given two numbers, but they've told me in a way that it's the same number. So they say my 0 is 2, so I am going to use 2 out here, but with a multiplicity of 2, which basically means I'm going to be using 2 twice. So x to the fourth is the highest, so put his coefficient, then x cubed. But I don't have an x cubed, so I have to fill it in with a 0, then the coefficient for x squared, then the coefficient for x, and finally the coefficient, or the constant. Follow your synthetic division process. And here's where it gets a little bit different. Notice I don't have 3 numbers to do the A, B, and C, right? We have 4. So we've got to shrink this down to just 3 in order to do the quadratic formula. And since they gave us 2 zeros, we're going to use the second one. Now, if they're explicitly given like this, then you just use one of them first and then use the other one next. And it doesn't matter what order you do them in. Here, I'm given the same number twice, so I'm just going to do this whole process again with that same number again. So 2 again. Follow your synthetic division. And I get 0 as my remainder, and I get my A, my B, and my C for my quadratic formula. So my quadratic formula is going to be square root of 36 is 6, but the negative comes out as an I. So we get negative 2 plus or minus 3I. So here are your zeros. You have 2, 2 again, negative 2 plus 3I, and negative 2 minus 3I. We have an x to the fourth problem, so we should have 4 zeros here. And if you're going to write the function in factored form, it's going to be x minus 2, x minus 2, x plus 2 minus 3i, x plus 2 plus 3i. And the only thing here else I would do is just write the double with a square and then finish with the other two factors. That's the only formality you need to apply. And that's done.